Now, observers are a very key factor in terms of automating very large amount of systems, because this time we don't actually need a manual input. It just observes its surrounding and gives out a signal based off of it. The way you have an observer is that you can see that you have an arrow pointing outwards. This means that the redstone signal is going away from us. We can see that the eyes are at the back of the observer, which always observe a change in state, no matter what it is. So it's not necessarily looking for an on and off, it's just looking for a change in state. Once it identifies that change in state, you can see the arrow pointing backwards tells us that it's going to flow out a redstone signal. For example, on this block in front of it, if it does observe a change in state, then it will output a redstone signal, letting the redstone lamp light up. We can look at different examples of how a change in state is actually observed. For example, placing or breaking a block, opening and closing a chest. You can even strip wood, of course opening and closing the door, turning pages in a book. This shulker observes this sound, which of course changes the state to turn it on, allowing the redstone lamp to light up. You can even walk over redstone ore. Now keep in mind, containers themselves won't be able to have a change in state because physically nothing has happened. On the other hand, when we did open the chest or even this barrel here, we can see that when we do open it, this front bit is open in terms of its texture. So of course, since there's a physical state, then that means it powers on the observer, allowing it to output this redstone signal. Similarly with brewing stands, it is a container, but when we do place some items in it, for example a water bottle, we can see that it physically is there, which allows it for a change in state, powering the redstone lamp. But if for example we place a spider eye, you can't actually see the spider eye on the brewing stand, which means that there is no change in state. You can use bone meal on grass, you can hoe some sort of farmland, you can place bone meal on nylium, and even the change of state of a coral dying out. You can light a candle, and you can change the orientation of a glass pane. This also works for fences too. You can even walk over this string, which activates a change in state. So there is no need for a tripwire hook. Now keep in mind, there are various different examples, but these are just a few that might be prominent and something to keep in mind. Now if you let two observers observe each other, you can see that it creates an infinite loop. And as you can see, that the power constantly turns on and off, so there is no delay for it to turn off the redstone lamp, which means that these two redstone lamps will constantly be powered on. Now the target block seems quite self-explanatory, because you can tell that when you do hit the target, of course it's just going to power the redstone, as you can see. But there's actually much more of a use to it. We can use the target block for redirecting redstone. If for example we wanted to feed off redstone and place it onto this component here, instead of doing that, we can just use the target block itself, allowing the redirection of the redstone. This is useful for making circuits compact and much more efficient. An example where target blocks can be used to make compact designs is by using a 2x2 piston door as an example. So as you can see on the right hand side, we have this repeater feeding into this redstone torch, allowing it to turn off the pistons, letting us go through the doors when we do press the pressure plates. Whereas on the left hand side, we can see that we have the target block powered in, which redirects the redstone torch, turning it off, again turning off the piston doors. So we have the same contraction on either side, one is just more compact. But you can also see that on the right hand side, there's a very small delay, as opposed to using the target block, which is instant. This is because of the repeater causing this delay. So if you're looking for instant redstone, then the target block is much more useful in that case, as well as being compact. Now, there's two components, which is the dispenser and the dropper. A dispenser utilizes the item if it can be utilized, whereas the dropper always will just drop the item. So if, for example, we have an arrow which can be shot as in a projectile, if we were to power the dispenser, it shoots the arrow. Whereas if we powered the dropper, it drops the arrow. Now, if we did the same thing, but with a decorated pot, you can't actually utilize the item, so the dispenser will just drop it. Similarly, the dropper will always drop the item. The hopper can be used to extract items from a container. So if, for example, we place items in a chest, it will extract all the items in the chest right into the hopper. Now with hoppers, it's not only about extracting items from a container, you can use them to drop items into the hopper. For example, we didn't want the hopper to pick up any items when we do drop into it. We can set up this contraption powering this block, essentially powering this hopper, which locks the hopper. So if you were to drop any items into it, it doesn't go in. And if we do turn off the lock, the item will fall straight in. The same thing works when extracting items from a container. If the hopper is locked, which is right underneath the container, and we place items into it, none of the items will flow into the hopper because it's locked. Now, redstone comparators are, in my opinion, the most useful component because of how many systems and creations you can actually make with it and the different uses that it has. For example, we'll start off with the most obvious mode, is the comparing mode. In terms of the comparing mode, we need to first understand that it has three different inputs. So the rear end, and then the two sides. And of course the output is this front facing here. Now when we are comparing signals, all we're doing is this is our main input and we're comparing it with either of the side inputs. So if, for example, we have a rear input of 14 going into the comparator, it will now output that same power level 14 into the lamp. Now for the comparing factor, we use either side. So let's say, for example, we have an input of 12 going into the side of the comparator. Since 14 is greater than 12, we have an output of 14. Similarly, if we have an input of 10 going into the other side of the comparator, again 14 is both greater than 12 and 10, so it will still output a power level of 14. But if one side was to be larger than either one of the sides, comparing the rear input, we have a power level of 14 as compared to a power level of 12 or 15. We know that 15 is greater, so since 15 is greater, this will turn off the signal. So an easy way to think about it is this is your main comparison, and you're comparing it with either side of the inputs. If this is larger, then the redstone lamp will turn on. If it's smaller than either one of the side inputs, then the redstone lamp will turn off. Now the other mode is called the subtractor mode. Now what it does, it understands the rear input, which as we have in this example is 15, and we subtract it by the largest of the two values of the side inputs. So if, for example, we have an input of 12 going into the side on the right hand side, and we have an input of 13 going into the left hand side, we know that 15, if we're comparing it, minus one of the larger inputs on either side, which is 13 in this case, 15 minus 13 is going to be 2, so we're going to output a signal of 2. Now since we need an output of signal 3 to power this redstone lamp, it means that the redstone lamp won't be powered on since the redstone signal doesn't actually reach it. Now let's say we extend this side input so that we have an input of 10 and we have an input of 12 on either side, and of course we have 15. 12 is larger than 10, so that means we do 15 minus 12, which gives us 3. 3 is the power signal required to power this redstone lamp, which means that it will turn on. the rear input was to be much smaller, for example 13, and let's say the side input is 14, this means that we will have 13 minus 14, since it's larger of the two side inputs, which will give us a negative value, which means that there will be no power supplied to this redstone lamp. Now, another way comparators are used is by comparing the state of the block. Most commonly, those blocks should be classified as containers. So if, for example, we're comparing the state of the container, in this case a chest, depending on how full it is, will show us the signal strength of the redstone. So if, for example, we fill it a third full, we can see that it gives a power output of 5. The way that you calculate the power output of these containers is you find the decimal percentage of how much is filled out, which is 0.33, since it's a decimal percentage, and then we multiply by 15. That value gives us 5, which shows on this redstone line here, giving us a power output of 5. And of course, if we were to fill it out another third more, that should give us a power output of 10. Now, there's many different blocks that can be classified as containers. For example, a lectern holding a book, and depending on the amount of pages you have in the book will tell you the signal strength of the redstone. Another one is a hopper. Again, depending on how many items there are, will tell you how powerful the redstone signal is. A cauldron, a brewing stand holding water bottles, a crafter holding items, a bookshelf holding items, an item frame, a chiseled bookshelf holding books, a composter which holds compost, a barrel holding items, and even a smoker holding items.